Hey guys, today we're going to start looking at section 3.9, which is on related rates. This is a neat application of calculus. The idea here is whenever you have two quantities that are somehow related to each other, if one of those quantities starts changing, then the other one is also going to change, and there's going to be some relationship between the way or those two rates of change. I think one of the most common things to think about for this, common examples, would be blowing up a balloon. You know how when you blow up a balloon at the start, when you blow it up, it increases you're increasing the volume of the balloon. But if you think about the diameter, the diameter in the beginning it grows quite a bit, but toward the end, when the balloon's getting really big, then the diameter is not going to increase very fast. The rate of change of the diameter is going to slow down. And here's a video of a guy blowing up a balloon. See, at first, in the beginning, it goes from nothing to a sphere pretty quickly. And then toward the end, the diameter is not changing nearly as fast as it was at the beginning. You know, if you were blowing this up, just manually, at the end, it starts getting bigger, slower and slower, and there's that tension you're worried that's going to pop in your face. So anyway, we can use calculus to look at the relationship between how fast the volume is changing and how fast the diameter or the radius or even the surface area is changing. So what I want to do is start with a simple example. Let's say you've got a square on a computer screen. And I'm going to call the length of the thing x, and the area is, of course, x squared. But let's say this thing is growing at some rate. As it grows, the area grows and the length grows. So the example says the square is growing at a rate of 2 millimeters per second. That's the length. That's how fast the length is changing. Now, the question asks, how fast is the area growing when x is 25 square millimeters? So let's look at this. The idea behind this is you want to treat both length and area as functions of time and use the chain rule. So A is the area. I'm going to come down here and sort of label this stuff. A is the area. dA dt is the rate of change of the area. So the variable t, we're not really going to do much with it in this problem, but we will use it as on the bottom of our derivatives because we're looking at the rate of change of area with respect to time. And likewise, x is the length, and dx dt is the rate of change of the length. So this equation up here, a equals x squared, that relates the quantities. If we take the derivative of this with respect to time, then we'll get the rate equation, which relates the rates. Now the derivative of a is 1, but then we have to multiply by its derivative with respect to time, dA dt. The idea there is we're doing this as an implicit derivative, and everything is a function of time. On the other side, derivative of x squared is going to be 2x, but we have to multiply by the derivative of x with respect to time. And this is our rate equation. That's the thing we're going to plug into in the end to answer the question. The question was, well, before we do the question, let's look at what they tell us. They say the square, the length is changing at a rate of 2 millimeters per second. So what they're telling us there is dx dt is 2. And what they're asking us here, how fast is the area growing? They're really telling us to find dA dt when area is 25. So what we've got to do is just plug into the rate equation and solve for dA dt. Let's see, so dA dt is equal to 2 times x times dx dt. Okay, when a is 25, if the area is 25, then x is 5. So this is a 5. And then dx dt is 2. So we get that. So all I'm doing is I'm taking this equation, I'm plugging stuff into it. So I wind up with dA dt is equal to, well, it's 20, and the units here will take care of themselves. This is talking about how fast the area is changing. So this is going to be 20 square millimeters per second. And it's important to note one thing. dA dt is 20 when x equals 5. That rate of change, how fast that rate of change is, that's going to change during, throughout the problem. As the square gets bigger and bigger, the area is going to grow faster and faster. And so when I put this here as my answer, dA dt equals 20, that is specifically at this instant in time that they're asking for. So let's look at this problem-solving strategy. This came out of the textbook. I don't know exactly which page, but somewhere in section 3.9. But let's look at what it says. Read the problem. Draw a diagram. That's going to be useful in most of these, to draw a diagram. Introduce notation. We did that here by putting in the x and the a. Express the given information in terms of, and the required rate in terms of derivatives. So that involved two things: coming up with the relation among the quantities, and then taking the derivative there. Actually, I'm getting a little ahead of myself. Express the given information and required rate in terms of derivatives. That's what I did up here when I said dx dt is 2. We're supposed to find dA dt here. After that, we find we write the equation that relates to the quantities, then use the chain rule to differentiate both sides, and then substitute the stuff back in. And that lets us find the unknown rate. So what I want to do here is I want to do several examples. And I don't want the videos to be terribly long, so I'm going to break this up into several videos. But maybe I should go ahead and do one more example in this video. Let's look at this one. A rock is dropped in a pond, creating a circular ripple. So you drop the rock and then the ripple gets bigger and bigger. So the question is asking, says the radius of the ripple increases at 2 meters per second. How fast is the area of the circle increasing when the radius is 10? All right, so for this, what we have here is area of a circle is pi r squared. They tell us the radius is increasing at 2 meters per second. So that tells us dr dt is 2. And they want us to find dA dt when r is 10. All right, so I've already got the equation up there that relates area to radius. If I take its derivative with respect to time, the derivative of a is 1 times dA dt. Derivative of pi r squared. Now r is my variable. And remember, pi is just a constant. So derivative of that's going to be 2 pi r and then times dr dt. So that's our rate equation. And we're supposed to find dA dt when r equals 10. Well, we've got everything we need to solve it. So dA dt is going to be 2 pi, r at this instant in time is 10, dr dt is 2. So what do we get there? 40 pi, and the units are going to be meters per second. So the basic sort of setup for these problems, they all are very similar. Some of the problems get a little more involved later because sometimes it's difficult to set up what that original relationship is. Sometimes we'll have to use geometry, maybe use some similar triangles and things. On a problem like this, or the problem with the square, it's pretty simple, where you just have a formula. But we're going to do a bunch of examples where some of them are more difficult and some of them are going to be easier. So we'll pick up here in the next video.